Welcome to Intermediate Algebra, Chapter 3, Section 1. This was formerly known as Chapter 4, Section 1, so there was a little bit of confusion, but I think we've got all that straightened out, and what we're going to look at in this section is, in this chapter, really, we're talking about systems of equations, and in this section, we're going to look at a system of two equations in two variables, and we're going to see about solving these systems graphically. I generally speaking don't recommend solving a system of equations graphically because your solution's only going to be as accurate as your graph. And if you're graphing using pencil and paper, or even if you're graphing on a computer, again, the graph can only be so accurate. Plus, graphs are going to eventually get complicated enough that solving them graphically is going to be very cumbersome, and we'll prefer to switch over to an algebraic process. But for the moment, let's have a look at how to do it graphically. There are three different scenarios that we can run into when we are trying to solve a system graphically. The first possibility is that the two lines that represent the two equations that we're working with are going to intersect at one point. And if they intersect at one point, the two equations, or the system as a whole, is considered to be a consistent system because there is at least one solution. The equations themselves are considered to be independent equations. The only time that we'll call them dependent equations is if the two equations, although they may look different, end up describing the same line. The second scenario is that our two equations describe lines that are parallel to each other. These two lines are clearly independent. They don't intersect at all. And because they don't intersect at all, there's no solution. They have no point in common. And therefore, we will say that this is an inconsistent system. In our third scenario, where our two equations end up describing the exact same line, since they do have, or since there is more than one solution, more than one point of intersection, we'll say that this system is consistent because there's at least one solution or at least one point in common on the two lines. But because the two lines are really the same line, we're going to say that these equations are dependent. What does it mean for a system of equations to have a solution? What it means is that there is a point, or potentially more than one point, that satisfies both equations. And number one here gives us the opportunity to demonstrate that. We're asked to determine whether the ordered pair 2, -1 is a solution to the system. It's very easy to make that determination. We simply plug in these x and y values into both equations and see if it turns out that both equations are made true. So into our first equation, we have 3 times 2 equals 5 minus our y value of -1, and 6 does equal 6. So far, it looks like this is a solution to the system. In our second equation, we've got 2 times our x value of 2 equals 1 minus 3 times our y value of -1. The left-hand side of our equation equals 4. The right-hand side of our equation with that double negative in there says 1 plus 3, which equals 4 also. That equation has also been made true by this ordered pair. So we can say that this ordered pair, 2, -1, is a solution to the system. Graphically, it would be the point of intersection of these two lines. And that's what we're seeing in problem number 2. So we're given two equations, and they are already graphed for us on the right there. And the first request is that we solve the system by graphing. And the solution to the system is the point of intersection. So all we have to do is zoom in here a little and see that the point of intersection happens at 3, 5. And we can say that the solution to the system is 3, 5. And if you'd like to include maybe equals x comma y, just so that you don't mistakenly think for some reason that that's an interval, it is an ordered pair. Identify whether the system is consistent or inconsistent. It's consistent because there's at least one point of intersection. In other words, there is at least one solution. So it's consistent. And is it dependent or independent? These lines are independent. The only time that they're classified as dependent is if the two equations are actually describing the same line. So we're going to see all three variations here. This system of equations, if we graph it, turns out to be a pair of parallel lines. We cannot solve the system, or the solution is no solution, because there are no points of intersection. No solution. There are many ordered pairs that would satisfy this equation, and there are many ordered pairs that would satisfy this equation. However, there's no ordered pair that we could do like we did in the first example, where we could plug the ordered pair into both equations and have both of them be true. So therefore, there's no solution. The system is inconsistent because there is not at least one solution. And these equations are independent. They don't even touch each other. They're very independent. Again, only dependent if the two equations are describing the same line, as is the case here in number 4. Let's work this one from the bottom to the top. The equations are dependent, we would say, because they describe the same line. Is the system consistent or inconsistent? There's at least one solution. There's at least one point of intersection. In fact, there are infinitely many points of intersection, with those two lines being right on top of each other. And to solve the system by graphing, the solution to this system really is the entire, or either one of these equations. I would tend to use the first one. You could phrase your solution to this as the set of ordered pairs x comma y such that 3x plus y equals 10. And this bar right here, that's where I said such that, is just that. It's just a vertical bar. There's even a key on the keyboard of your computer probably. On mine, above the enter button is a slash, the forward slash, and then above that is a vertical line. And if you hit shift, you could access that, and it would put in a vertical bar for you. Hopefully, if you're typing this into online software, there will be some sort of like a little toolbar with the infinity symbol and the pi symbol and things like that, and that'll give you access to a vertical bar to make sure that it works correctly. And that's it. Those are all three scenarios. Again, because solving systems of equations graphically is infrequently the method for solving a system of equations, this is not a long section. So go in and check out a couple of practice problems in a homework assignment, and I will see you in the next section where we're going to start using some algebraic processes in order to solve systems. See you there.